Hey guys, we're going to do a little recording on solving problems 5 and 6 on the train math. I think those two problems are good because they're an example of how you use math in everyday life. So, plus, we all struggled. I think only one person got those 100% right. So, let's look at the page. If I can find it, then there it is. However, you're still just seeing me. So let's go to present. And here we are. All right. So problem number 5 wants to know the least amount of time. Problem number 6 wants to know the longest amount of time. So what we're going to do is set up our page so that we have both circumstances. We're going to have the worst case scenario, which is the longest period of time. And we're going to have the best case, which is the shortest. The shortest is actually problem number 5. The longest is problem number 6. Okay, so let's look at what the story problem tells us. First off, at 7 a.m., we load the train with logs, which might take 1 or 1.5 hours. So if we look at the worst case scenario, we're looking at the 1.5 hours. If we break that down into hours and minutes, that's going to be 1 hour, 30 minutes. For the worst case scenario, the best case scenario is 1 hour. I'm just going to show you what my paper looks like. I've got, this is for loading. When you're doing a problem like this, it's a really good idea to label each thing. That way you know that you haven't left anything out as far as important details. All right, let's go back to our problem. Okay, then we head for the mill. It's only about 10 miles away, but we've got some pretty good hills between here and there. The train generally goes 10 to 15 miles per hour. So, looking at our paper, when the train goes 10 to 15 miles an hour, which one's going to be slowest, the 10 or the 15? It's sort of like if you're going to Wichita, you probably drive around 60 to 70 miles an hour. Obviously, 70, you're going a lot faster, more miles per every hour. 60, 10 less out. So in our problem, our worst case is that we're going 10 miles per hour. Our best case is that we are going 15 miles per hour. And we know that it takes, let's see, they said that it's 10 total miles. So if it's miles per hour and it's 10 miles, one thing that we have to think about here is, even though this is how we do speed, if we're dealing with 10 miles, if we do our multiplication like this, our miles aren't going to cancel each other. They're going to square each other, and that's not what we want. So what we want to do is we want to take our 10 miles and flip this ratio so that we have in 1 hour, we go 10 miles. That way, our units will cancel out, our numbers will cancel out, and we know that our transit is going to take 1 hour exactly. So the trip in the best or in the worst case scenario takes 1 hour. In the best case scenario, we do the same thing. We know that we are going for 10 miles. We know that we need the miles to be on the bottom, so we're going to flip this and say that we have 1 hour that passes for every 15 miles. Our units cancel, and we end up with 10/15 of an hour. That looks pretty ugly. We don't want to leave it like that. What we want to do is convert it into minutes. So if I have 10/15 of an hour and I want to convert it, I know that I need to multiply it by something that cancels with hours. And since we want it to be in parts of an hour or minutes, we're going to put the number of minutes there are in every hour on top of this ratio. So, how many minutes is in an hour? You could count it by fives if you're looking at a clock. You could look it up on Google. But hopefully, most of us know by now that there are 60 minutes in every hour. Now that we have this set up, our hours are going to cancel. Minutes can't cancel and that's what we wanted. We wanted to have minutes left over. So we want to look at 15 will go into 60. It will go 4 times. And then all we have to do is take our 4 times our 10, and we get 40 minutes. So I'm just going to put little boxes around the things that we know so far. We had 1 hour and 30 minutes and an hour. We had 1 hour, and then we had 40 minutes. The next thing we want to do is make sure that that is visible. And then we're going to go back and look at our story problem again. Okay, so if it's raining, which is going to be a worst case scenario, or there are wet leaves on the track, they start sliding. So they double the hills, which means they have to go up and down twice. The reason that they're doing that is because they're taking cars off to the side so that they have fewer cars weighing them down. This says that that takes a half hour. That half hour only exists in the worst case scenario. So half an hour, half of 60 is 30. We are going to add 30 minutes to our worst case scenario, which we said is right on the left-hand side. So we scroll up here. We're going to say that wet conditions add 30 minutes to our time. But we don't add that to our best case scenario. All right, back to the story problem. There's a lot of back and forth on this. That's kind of the way math works in the real world. All right, at the mill, they swap cars. This procedure takes about 20 minutes. The 20 minutes exists no matter what. So we're going to say swap. That takes 20 minutes in both cases. And back to the story problem. If we're carrying empty cars, the trip takes back only 20 minutes. That's going to be our best case scenario. So over here, under our best side, we are going to put return trip. In the best case, it was 20 minutes. Now we want the worst case. In the worst case, that's when the cars are full. And that trip takes 70 minutes. So over here, worst case side, we have 70 minutes. And let's look and see if there's anything else we have to add. Nope, that is the last of it. Okay, so we need to run some numbers and figure out what we've got here. On our left-hand side, we had an hour 30 plus an hour. So I'm going to write the summary down here. I have an hour. Here's our hours. Here's our minutes. I'm going to do that on both sides. Okay, so I had an hour 30 for the loading. Then I had an hour for the trip. Then I had 30 minutes plus 20 minutes and then 70 more minutes. So I've got 30, 20, and 70. On my other side, I originally had 1 hour, then I had 40 minutes. So I'm just going to put that down as 1 hour, 40 minutes. Then I had 20 and 20. So 20 and 20. All right. Clumping things into groups that help us out is the best way to work problems like these. When we see that we have 30 and 30, we know automatically that those go together to give us 1 hour. Then we have 70 plus 20. That's a total of 90 minutes. We know that 90 minutes can be broken down into 60 minutes and 30 minutes. We know 60 minutes is 1 more hour, and 30 minutes is all that's left. Over here, where we've put all of our hours, we have 1, 2, 3, 4 hours and 30 minutes as our worst case scenario. Worst, slowest. Okay, well, let's look over here. We know that 40 plus 20, once again, is 60, so we can take that off and make it an hour. We don't have any other minutes, so we know we have 20 minutes. And then we have 1, and 1 is 2 hours and 20 minutes for our best or fastest time. Make sure that you put your units on. Otherwise, things don't make any sense if it's just random numbers. It could be minutes, it could be hours, and anybody who's sat through a minute or an hour knows there's a huge difference. Just remember that this is problem number 5, and this is problem number 6. And you can use this kind of method of breaking things down on just any kind of problem like this. And we're going to do that on the next problems that we do. So, thanks for hopping on here. And we'll do the next ones on the next video. Thanks a lot.